This week, we're going to learn a new technique to see how well our machine learning algorithm is generalizing to our data set. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week, we're going to look at cross-validation, which is a technique that we use to see how well our algorithm or our trained method that we're using has generalized the data set. So we've learned all about how to use accuracy and recall and precision and F1 scores and R squared to see how well it worked with a test-train split. This is a little more advanced method. It takes a little more compute power, but it gives you a much better idea of how well that given trained algorithm with those parameters is going to work in the real world. It does not actually return a trained instance of any neural network object or classifier to you, though, because the goal is not for it to do that training. The goal is for it to evaluate how that model with those parameters is going to work. Cross-validation can be done in a number of ways. We're just going to look at a couple of popular ones. First off, and the most common one, is the k-folds cross-validation. In k-folds, we just take our data and chunk it up into k pieces. So let's say we're doing a 3-folds cross-validation. We would split our data into thirds, or as near to thirds as we could get it. We would then hold the first data set out for testing and use sets 2 and 3 for training. Then we would hold data set 2 out and use set 1 and 3 for training. And then we would hold data set 3 out and use 1 and 2 for training. So we would train 3 instances of whatever technique we're using, and then we would get a score for each of those. And if some of the scores are very high and some of the scores are very low, that tells you that it's not generalizing well. It's very sensitive to what data it is trained upon. That could be an artifact of the data, or it could be an artifact saying you've got too little data. That's almost always the answer in any machine learning problem, is go get more data. So k-folds has some limitations. Just straight k-folds, well, if your data have any order to them, say the classic iris data set, then you're getting all of case 0 and the first fold and all of case 1 and the second fold. So it's not going to generalize well, but that's totally artificial in that case. In that case, we can use stratified k-folds. When we add the stratified qualifier, that means we're going to keep the proportion of classes in each field. So for example, if we had 80% no rain and 20% rain, thinking about our data that we've been using, we're going to keep that same proportion in fold 1, fold 2, and fold 3. In fact, this is the default method that scikit-learn uses when it's computing a cross-validation score. For classifiers only, though. If you're using a regression problem, it defaults to the simple k-folds. You can, of course, go in and change that, but it will default based on what type of algorithm you're using, a regressor or a classifier. So let's actually do this. From sklearn.model selection, I'm going to import cross-val score. And like many things with scikit-learn, the actual code is somewhat anticlimactic here. There's a lot more theory to learn behind it than anything else. So what I've done is called the cross-val score method, given it our classifier object. So the model, not necessarily trained, just the model with the parameters that we're going to use. Then our x and our y vectors, so our feature vector and our answers, or our targets. And I told it that we want 5 folds. Now if we look at the scores, we can see we've got 80.1, 80.3, 81.1, 82, 81.2. So they're all relatively close together. And often you'll see in papers the mean score of the k-fold scores reported. So in this case, 80.9. So how does that compare to what we saw looking at other methods? Well, don't forget we have the classification report. We can use our y-test and y-pred from the classifier and get a classification report on it. All right, our accuracy, F1 score, 87, 84, yep. So we actually are in the neighborhood most of the time. But this is a really nice way to know if you saw everything from, say, 60 to 100 here, you know that you're really training data sensitive, and that could be a problem. Now, there are two more methods, and we're only going to look at one of them. The shuffle cross-validation. So doing shuffle, we're going to draw randomly from the data set to create the folds without replacement. This is really great because you can specify how much of the data we want to use for our test and our train. So it lets you use less than all of the data if you want, if those numbers don't add up to 1. What's really convenient then is if you have a huge data set and you just want to play around with some different classifiers, you can use this to work on a smaller subset of that data. Most of the time, especially in our field, we don't necessarily have that problem, but that is an available option. So from the sklearn model selection, I'm going to import the shuffle split. So I'm going to create an instance of the shuffle split object called shuff. Going to tell it that I want to do 5 splits. You can draw an arbitrary number here though. Another nice feature of using the shuffle split. I'm going to use 25% of the data for our test size. I'm not going to specify a train size. That just means that we'll use the balance. Again, you could make those two less than 1. And if you want to, you can specify a random state so that others can reproduce your work. We're going to now create scores. I'm going to call the same cross-val score function, the same classifier, the same feature vector, and the same target vector, but now we're going to say CV equals shuff, so we can actually pass complete instances of splitting objects here. So now it's going to go through, compute our scores after doing the shuffle split. We'll print the scores, and we'll print the mean of the scores as well. Now, while that's computing, the one method that we're not going to mention, our other popular method anyway, that we're not going to mention, is the leave one out method. This is great if you've got a very, very small data set. Leave one out has a test size of 1. You pull one data point out, you train on everything else, and you see how you did. And you do that for every data point. That takes a very long time for large data sets, but if you do have a smaller data set, it can be one method that may give you a better idea than something like a shuffle split or a k-folds with very many folds or enough to be useful. So here we've got our results, and we see that they're all in the neighborhood of 81 point something. So maybe this is a good method, or maybe, well, for our data that's very imbalanced, maybe we want to keep those proportions, so a stratified k-fold, but either way, they're all within about 1%. And the mean is 81.5. I hope that you found this useful and that you're going to go and check some of your algorithms that you've tried with these different splits and cross-validation techniques. I hope that you found this useful. I'll see you on next week's MetPy Monday.